Welcome to the GPWS lesson in the PMDG 737 Next Generation Groundwork from Angle of Attack. This lesson will cover the following topics. We'll start with a brief overview of the background, objectives, and functions of the GPWS and eGPWS systems. We'll cover the Ground Proximity Warning Computer, or GPWC, the GPWS operating modes, the GPWS enhanced functions, the navigation display terrain display, and we'll run through the controls and indications relating to this system. We'll finish up, of course, with a lesson summary. GPWS stands for Ground Proximity Warning System, and eGPWS stands for Enhanced Ground Proximity Warning System. Both systems are designed to help prevent accidents caused by CFIT, or controlled flight into terrain. A CFIT accident occurs when an airworthy aircraft, under the control of a pilot, is flown into terrain, water, or obstacles with inadequate awareness on the part of the pilot of the impending disaster. Following a string of deadly CFIT accidents in the 1960s and a subsequent inquiry into what could be done about it, the original GPWS system was developed and subsequently made mandatory for Part 121 aircraft by the US FAA in 1974. The original GPWS systems had a critical weakness, however. They used the radio altimeter as their core reference, which only monitors terrain directly below the aircraft. Very steep rising terrain could therefore trigger warnings far too late for the pilots to react in time. A more advanced system, Enhanced GPWS or eGPWS, was developed during the 1990s by Honeywell. Enhanced GPWS was introduced in 1996 and uses GPS-derived positioning information married to a digital terrain database to overcome the limitations of the earlier GPWS systems. This allows the system to look ahead of the aircraft and anticipate collision risks well in advance of projected impact, and this has been instrumental in increasing air safety over the past decade. The database also allows for terrain data to be displayed on the navigation display, greatly increasing situational awareness. The 737 Next Generation is equipped with enhanced GPWS, so we will be talking at length about the extra features that it adds later on. The heart of the GPWS on the 737NG is the Ground Proximity Warning Computer, or GPWC. The GPWC is located in the electronic equipment compartment, top left on the forwardmost shelf as you look forward. It receives inputs from many systems and components on the aircraft, including the Air Data Inertial Reference System, the Stall Management Yaw Damper computers, the radio altimeters, the multimode receivers, the Flight Management Computer System, the Mode Control Panel, the Display Electronic Units, the Weather Radar, and the Ground Proximity Warning Module. The GPWC uses these inputs to generate alerts and terrain data on the navigation display. The GPWC also outputs data to several aircraft systems, including the display electronic units, terrain and weather relays, and the flight data acquisition unit. Additionally to performing calculations for the generation of GPWS alerts, the GPWC also incorporates terrain and airport databases used by the GPWS enhanced functions. We discuss these databases in greater detail later in the lesson. GPWS is a very versatile system available on many types of aircraft. The model of GPWC installed on the 737 Next Generation is also available on other aircraft types, so a number of program pins are used to define the operational environment of the system. During installation of the unit, program pins are positioned to specify several parameters, including aircraft make and model, electrical interfaces, and feature selections. Airlines may adjust GPWS features such as the range of Mode 6 approach callouts to suit their operation and SOPs. Many more customizations are possible, of course. These selections are made on the ground by maintenance via program pins on the GPWC, and these are not pilot alterable. The ground proximity warning system on the 737 Next Generation monitors and provides alerts for 7 different sets of conditions. There are also several enhanced functions introduced in the 1990s with eGPWS, and we cover the enhanced functions in the second half of this lesson. We will first discuss the 7 classic GPWS operating modes, and these modes are as follows. Mode 1, excessive descent rate. Mode 2, excessive terrain closure rate. Mode 3, excessive altitude loss after takeoff or go-around. Mode 4, unsafe terrain clearance. Mode 5, excessive deviation below the ILS glide slope. Mode 6, advisory callouts. And Mode 7, reactive wind shear. Modes 2, 4, and 6 have various submodes that we will discuss in detail later. Before we dive into our explanations of the various operating modes, let's clear up the difference between radio and barometric altitude, as we will be using both terms throughout our discussion of the various modes. We'll start with barometric altitude. Atmospheric pressure drops with an increase in altitude. The aircraft's barometric altimeters use those changes in atmospheric pressure to indicate altitude. Barometric altitude is therefore a distance above a predetermined datum, usually sea level. This altitude is indicated on the PFD altitude tape. Radio altitude is determined by transmitting radio waves downwards beneath the aircraft and timing how long it takes them to be reflected back again. Because the speed of these waves is a known quantity, the distance can then be calculated to determine radio altitude. Radio altitude is therefore the altitude above the terrain directly beneath the aircraft. It is important to understand these differences as the GPWC uses both barometric and radio altitude as inputs. The GPWC also uses inertial altitude as an input for modes 2 and 3. Inertial altitude is an ADIRU-derived altitude used by several aircraft systems, including the flight control computers, the flight management computers, and the GPWC. We'll run through the GPWS operating modes starting with Mode 1, excessive descent rate. Mode 1 provides alerts for excessive descent rates with respect to altitude above ground level. The descent rate input for Mode 1 is inertial vertical speed, or IVS. This is an ADIRU-derived quantity not prone to the lag of barometric vertical speed. If inertial vertical speed is not available for Mode 1, the GPWC uses an internally calculated altitude rate. If both the IVS and the inertial calculated rates are invalid, the barometric altitude rate from the Air Data Inertial Reference System is used. When barometric altitude rate is used, the base of the Mode 1 envelopes changes from 10 feet to 30 feet. The rate of descent at which an alert is triggered is dependent on the current radio altitude. The greater the radio altitude, the greater the rate of descent needed to trigger a Mode 1 alert. Mode 1 has 2 alert envelopes, a caution envelope and a warning envelope. Envelope dimensions are defined by radio altitude and descent rate. The greater the radio altitude, the greater the rate of descent needed to trigger a Mode 1 alert. Should an excessive rate of descent develop for the aircraft's current radio altitude, a oral caution message will be triggered. This occurs in the caution envelope. If the rate of descent continues or worsens, a continuous oral warning message will be triggered once the aircraft enters the warning envelope. When any Mode 1 alert is triggered, Pull up enunciates red on the primary flight displays as a visual alert. The pull-up visual alert is also relayed through the head-up guidance system, HGS, if installed. Mode 2 provides alerts for rapidly rising terrain with respect to the aircraft. This detection is based on the current radio altitude and the terrain closure rate. Terrain closure rate in this case is a rate of change of radio altitude, and this differs from descent rate monitored by Mode 1. Mode 1 is based on the rate of change of barometric altitude, while Mode 2 is based on the rate of change of radio altitude. A positive closure rate means that the aircraft is rapidly approaching the ground, as sensed by the radio altimeter. Mode 2 exists in two forms, 2A and 2B. These two submodes are selected as a function of flap position. Mode 2A is active when flaps are set less than 30, and Mode 2B when flaps are set at 30 or 40. Mode 2A provides alerts for excessive terrain closure rate during climb out, cruise, and initial approach with flaps 25 or less, and glide slope deviation more than 2 dots. Mode 2A has two alert envelopes, a caution envelope and a warning envelope. Envelope dimensions are defined by radio altitude and terrain closure rate. The greater the radio altitude, the greater the terrain closure rate needed to trigger a Mode 2A alert. The size of the 2A alert envelopes is dependent on airspeed. At higher airspeeds, the time to impact will be reduced, so the envelopes expand to provide increased alert times. For airspeeds less than 220 knots, the caution envelope tops out at 1,650 feet radio altitude. For airspeed greater than 220 knots, the envelopes expand to a maximum of 2,450 feet. If the aircraft penetrates the Mode 2A caution envelope, a terrain caution message is generated. If the condition is not corrected and the aircraft penetrates the Mode 2A warning envelope, a
pull up
warning message sounds and is repeated continuously until the aircraft exits the warning envelope. Once the aircraft has exited the Mode 2A envelopes, pull up continues to show on the PFD until barometric altitude has increased by 300 feet or after 45 seconds has elapsed. A
terrain
oral caution message will sound during this period if radio altitude continues to decrease. Mode 2B provides alerts for excessive terrain closure rate when the flaps are in the landing configuration 30 or 40. It is also active for the first 60 seconds after takeoff. The Mode 2B envelope is desensitized to permit normal landing approach maneuvers close to terrain without triggering unwanted alerts. It is inevitable during approach and landing that the aircraft will approach terrain, and in some cases, the runway thresholds may be in close proximity to rapidly rising terrain, resulting in radio altitude spikes on approach that could potentially trigger nuisance alerts. The Mode 2A alerting envelope could potentially trigger nuisance alerts during this phase, so Mode 2B is automatically activated upon selection of flaps 30 or 40, or once established on an ILS approach with a localizer and glide slope deviation less than 2 dots. This reduces the potential for nuisance alerts during an approach. Mode 2B is also active for the first 60 seconds after takeoff to prevent nuisance alerts during this period. Mode 2B has a single envelope. Envelope dimensions are defined by radio altitude and terrain closure rate. The greater the radio altitude, the greater the terrain closure rate needed to trigger a Mode 2B alert. The upper limit of the envelope is fixed at 789 feet radio altitude, but the lower limit varies between 600 feet and 30 feet as a function of inertial vertical speed and flap configuration. If the aircraft penetrates the Mode 2B envelope with either the gear or the flaps not in the landing configuration, a
terrain
oral caution message is generated. If this condition lasts for more than 1.6 seconds, a
pull up
oral warning message will sound. If the aircraft enters the envelope with the landing gear down, there will be no oral pull-up messages, but a
terrain
message will be repeated until the envelope is exited. When any Mode 2 alert is triggered, pull-up indicates red on the primary flight displays as a visual alert. The pull-up visual alert is also relayed through the head-up guidance system if installed. Mode 3 provides alerts for excessive altitude loss after takeoff or during a go-around below 240 feet. There is a single Mode 3 envelope, and envelope dimensions are defined by radio altitude and altitude loss. The altitude loss permitted is a function of radio altitude. The greater the radio altitude, the greater the altitude loss needed to trigger a Mode 3 alert. If the aircraft penetrates the Mode 3 envelope, a
don't sink
oral caution message is generated. The
don't sink
oral message is enunciated twice for each 20% degradation in altitude. The message will cease once a positive rate of climb is established. When a Mode 3 alert is triggered, pull-up enunciates red on the primary flight displays as a visual alert, and this alert is also relayed through the head-up guidance system if installed. Mode 4 provides alerts for insufficient terrain clearance with respect to phase of flight, aircraft configuration, and speed. Modes 1 and 2 are based around rates of descent and terrain closure, while Mode 4 prevents inadvertent flight into terrain where the rate of descent or terrain closure is too gradual to trigger a Mode 1 or 2 alert. Mode 4 exists in three forms: 4A, 4B, and 4C. These three modes are selected as a function of gear and flap position and phase of flight. Mode 4A is active during cruise and approach with the gear up and the flaps not in the landing configuration. Mode 4A provides alerting for inadvertent flight into terrain where the aircraft is not descending excessively and terrain closure is not excessive. Mode 4A has two alerting envelopes, and envelope dimensions are defined by radio altitude and computed airspeed. Below 500 foot radio altitude and less than 190 knots airspeed, the Mode 4A oral alert is
too low gear.
Below 190 knots airspeed, the envelope upper limit is 500 foot radio altitude. Above 190 knots airspeed, the envelope is shaped by increasing terrain clearance and generates a different oral message. As airspeed increases, the envelope expands to incorporate greater terrain clearances. The envelope expands to 1,000 feet at 250 knots. This airspeed compensation ensures a more timely alert as the time to impact reduces at higher airspeeds. Above 190 knots airspeed, the Mode 4A alert is
too low terrain.
For either Mode 4A alert, further alert messages are generated for each 20% degradation in altitude. Mode 4B is active during cruise and approach with the gear down and the flaps not in the landing configuration. Like Mode 4A, Mode 4B provides alerts for inadvertent flight into terrain where the aircraft is not descending excessively and terrain closure is not excessive. Mode 4B has two alerting envelopes, and envelope dimensions are defined by radio altitude and computed airspeed. Below 245 feet radio altitude and less than 159 knots airspeed, the Mode 4B oral alert is
too low flaps.
Below 159 knots airspeed, the upper envelope limit is 245 feet radio altitude. Above 159 knots, the envelope is shaped by increasing terrain clearance and generates a different oral message. As airspeed increases, the envelope expands to incorporate greater terrain clearances. The envelope expands to 1,000 feet at 250 knots, and this ensures a more timely alert as the time to impact reduces at higher airspeeds. Above 159 knots airspeed, the Mode 4A oral alert is
Too low, terrain.
For either Mode 4B oral alert, further alert messages are generated for each 20% degradation in altitude. Mode 4C is active during the takeoff phase or during a low altitude go-around with the gear or the flaps not in the landing configuration. The Mode 4C envelope is constructed dynamically as the aircraft climbs, using radio altitude and computed airspeed to define the top limit of the envelope. During the takeoff roll, the minimum terrain clearance is 0 feet. As the aircraft climbs, the minimum clearance is increased to 75% of the aircraft's radio altitude, based on an average taken over the previous 15 seconds. This value is not allowed to decrease and forms the top of the Mode 4C alert envelope. The envelope is limited to 500 feet radio altitude for airspeeds less than 190 knots, and above 190 knots, the envelope expands to a limit of 1,000 feet at 250 knots. If the aircraft's radio altitude enters the envelope, a
Too low, terrain.
alert is generated. The alerts cease once the aircraft leaves the envelope. When any Mode 4 alert is triggered, Pull Up enunciates red on the primary flight displays as a visual alert. This is also relayed through the HGS if installed. Mode 5 provides alerts for excessive deviation below the ILS glide slope. Mode 5 uses radio altitude and glide slope deviation as its references. There are two levels of Mode 5 alerting: soft alerts and hard alerts. A soft alert occurs when the aircraft is below 1,000 feet radio altitude, with ILS deviation 1.3 dots or greater below the glide slope. In this case, a reduced volume
Glide slope.
audio message is triggered. A hard alert occurs when the aircraft is below 300 feet radio altitude, with an ILS deviation 2 dots or greater below the glide slope. In this case, a full volume
Glide slope.
audio message is triggered. As deviation below glide slope increases, additional
Glide slope.
alerts are generated at a progressively faster rate. Mode 5 alerts are enabled only when the aircraft is below 1,000 feet radio altitude, the localizer signal has been captured, the glide slope signal is valid, the gear is down, and a front course approach has been selected. The GPWC identifies a front course approach by comparing the aircraft's magnetic track to the ILS approach course. If the difference is less than 90 degrees, it assumes that a front course approach is being conducted and Mode 5 alerts will be available. If the difference is greater than 90 degrees, it assumes that a back course approach is being flown, so Mode 5 alerts will be inhibited to prevent nuisance alerts. The upper boundary of the Mode 5 envelope is affected by aircraft descent rate. For descent rates greater than 500 feet per minute, the upper boundary is set to the normal 1,000 feet radio altitude. A vertical speed greater than 500 feet per minute is to be expected on a normal ILS approach, so this is the normal condition. For descent rates less than 500 feet per minute, the upper boundary is reduced to a minimum of 500 feet radio altitude. Additionally, both hard and soft modes are progressively desensitized below 150 feet radio altitude to allow for normal ILS glide slope variations near to the ground. This reduces the possibility of nuisance alerts. A Mode 5 alert causes the below glide slope switch to illuminate on the left and right forward panels. Pushing this switch inhibits Mode 5 glide slope alerts when below 1000 feet radio altitude. Mode 6 provides advisory callouts based on barometric altitude, radio altitude, and bank angle. Mode 6 callouts include radio and barometric altitude callouts, the minimums callout and the approaching minimums callout, and bank angle callouts. The set of callouts used is selectable by program pins on the ground proximity warning computer. This allows airlines to customize Mode 6 callouts to their operational environment and SOPs. Mode 6 provides altitude callouts during approach based on radio and barometric altitude. Callouts are provided for
2500
or
radio altimeter, 1000, 500, 400, 300, 200.
the callouts at 1000
50,
feet
40,
and 500 feet
20,
are based
10.
on barometric altitude above the landing field's elevation. The rest are based on radio altitude. A smart 500-foot callout is also available, which sounds only during a non-precision approach. When the smart 500-foot callout is selected,
500,
is only called during a non-precision approach. It is removed from precision approaches. The GPWC determines a non-precision approach when glide slope deviation is greater than 2 dots or if a back-course approach is being flown. Mode 6 also provides callouts for decision height or minimum descent altitude based on the altitude set by the captain's minimum selector on the EFIS control panel. These callouts may be based on radio or barometric altitude depending on the position of the minimums reference selector. There are 4 callouts available, up to 2 of which will sound during an approach.
plus 100,
Sounds 100 feet above the DH or MDA.
approaching minimums,
Sounds 80 feet above the DH or MDA.
minimums,
Or,
minimums,
or
decision height,
sounds when passing through the DH or MDA. The
minimums,
callout has priority over the other altitude callouts. For example, if the DH is set to 200 feet and both
200,
and
minimums,
are valid callouts, then only
minimums,
will be called out at 200 feet. Mode 6 also provides bank angle callouts to advise of an excessive roll angle. Between 30 and 130 feet radio altitude, a
bank angle,
callout is generated when the bank angle exceeds 10 degrees. Above 130 feet radio altitude, the callout occurs at 35 degrees, 40 degrees, and 45 degrees of bank. The callout sounds once as the aircraft passes through each threshold. In other words, a callout will sound as the aircraft passes through 35 degrees, but will not be given again until the bank angle passes through 40 degrees. A further callout will then be issued when 45 degrees is exceeded. When any one of the thresholds is exceeded, the bank angle must reduce below 30 degrees for the system to be reset before additional bank angle callouts will be provided. If the rate of bank is so great that the next threshold is reached before the previous threshold's callout is complete, then no callout is given for the bypassed limit. The vertical extent of the bank angle alert envelope is limitless. Mode 7 is designed to provide alerts if the aircraft enters wind shear. The term wind shear refers to a sudden and drastic change in wind direction or speed over a relatively short distance along the aircraft's flight path. Most wind usually travels more or less horizontally, but under certain conditions can be provoked to travel in a vertical direction. The most dangerous phenomenon associated with wind shear is microburst, as it poses a great threat to aircraft on approach or shortly after departure. A microburst is a localized, very concentrated column of sinking cool air, usually emitting from the base of a thunderstorm. As the air strikes the ground, it spreads horizontally. An aircraft flying through a microburst will first see an increase in airspeed as it enters the zone of increased headwinds. It will also experience an increased sink rate as the sinking air pushes it down. As the aircraft flies through the core of the microburst, tailwinds start to increase, with a corresponding decrease in airspeed. The combination of reduced airspeed and the downdraft from the microburst may force the aircraft into terrain if prompt correction is not applied. Several airliners have been lost to this phenomenon. Mode 7 is designed to provide alerts if the aircraft enters wind shear. Two alerting envelopes provide either wind shear caution or a wind shear warning alert. Mode 7 wind shear alerting is based on rapid rates of change of headwind, tailwind, updraft, and downdraft. Note that this is an entirely different system to predictive wind shear. Mode 7 is purely reactive and provides alerts based on currently occurring changes, rather than conditions detected ahead of the aircraft. An increasing headwind and/or increasing updraft may result in the aircraft entering the wind shear caution envelope. This would trigger a wind shear caution alert, which generates a oral message. This would be indicative of the aircraft entering a microburst. A decreasing headwind, which could also equate to an increasing tailwind, coupled with an increasing downdraft, is a far more dangerous situation. This region is covered by the warning envelope, penetration of which will trigger a wind shear warning and the oral alert. When a Mode 7 wind shear alert is triggered, wind shear enunciates red on the primary flight displays as a visual alert. The wind shear alert is also relayed through the HGS if installed. The visual alert remains present for as long as the aircraft is exposed to conditions that place it in the warning envelope. Other inputs to the warning envelope include available climb performance, flight path angle, airspeed significantly different from normal approach speed, and unusual fluctuations in static air temperature. Mode 7 wind shear alerting is active under the following flight conditions. During takeoff from rotation until 1500 feet AGL, during approach from 1500 feet down to 10 feet AGL, and during a missed approach until 1500 feet AGL. Remember that GPWS Mode 7 is an entirely separate system to predictive wind shear or PWS. PWS uses the weather radar to look ahead of the aircraft at wind trends that signify the existence of wind shear. Mode 7 is simply reactive to current wind shear conditions. We'll move on to the second half of the lesson now and talk about the GPWS enhanced functions. Additionally to the 7 classic GPWS modes already discussed, eGPWS adds several enhanced functions. These enhanced functions are made possible by an internal database in the GPWC. The internal database consists of 4 general subsets: a worldwide terrain database, a frequently updated obstacles database, a worldwide airport database containing information on runways 3,500 feet or greater in length, and an envelope modulation database referenced by the envelope modulation function covered later in the lesson. The aircraft's present position is overlaid on these databases to determine proximity to terrain, obstacles, and areas that require envelope modulation. Terrain alerts are then generated accordingly. The GPWC determines aircraft position using inputs primarily from the GPS-1 system. Aircraft position from the GPS-1 system is the primary input. If GPS-1 position is not valid, GPS-2 position is used. The GPWC determines aircraft position using inputs primarily from the GPS-1 system. Aircraft position from the GPS-1 system is therefore the primary input. If GPS-1 position is not valid, GPS-2 position is used. When neither GPS-1 nor GPS-2 positions are valid, ADIRU position may be used for short periods. We will discuss the first of the 4 enhanced functions now, envelope modulation. Early GPWS equipment was plagued by nuisance alerts, which could cause pilots to distrust the equipment even when actual hazardous conditions existed. Certain airports around the world have terrain features and approach procedures that have resulted in nuisance or missed alerts in the past. With the introduction of the eGPWS Terrain and Airport database, it is possible to identify these areas and adjust the normal alerting envelopes to compensate. Envelope modulation uses the database to both desensitize and expand alerting envelopes where required to provide alerting protection consistent with normal approaches. Airports that require envelope modulation are stored in the envelope modulation database. Each affected airport has a snapshot area and an envelope modulation area, both defined by latitude and longitude. As the aircraft enters the snapshot area, the GPWC looks at several aircraft parameters to verify that all the data required for envelope modulation is valid and within tolerances. Monitored inputs include latitude, longitude, radio altitude, localizer deviation, magnetic track, selected runway heading, and barometric corrected altitude. Once the snapshot requirements have been verified, one or more of the GPWS modes can be modified upon entry to the envelope modulation area. The envelope modulation function adjusts the mode 1, 2, 4, and 5 envelopes to prevent nuisance or missed alerts. Mode 1 may be adjusted to allow for greater descent rates. Mode 2 may be adjusted to allow for greater terrain closure rates. Mode 4 may be adjusted to allow for less minimum terrain clearance. And Mode 5 may be adjusted to allow for glide slope warnings at higher radio altitudes, including with the landing gear up. The envelope modulation function is automatic and requires no flight crew action. The terrain clearance floor function alerts the pilots of a descent below a defined terrain clearance floor. The standard GPWS modes 2 and 4 are desensitized when the aircraft is in the landing configuration, and thus fail to trigger alerts when landings are attempted where there is no airport. Since eGPWS features a terrain and airport database which contains the exact positions of all allowable airport runways, it is possible to define an additional alert envelope at all areas where there are no runways. This is the terrain clearance floor. When the aircraft is 15 nautical miles or greater from a runway, the floor is 700 feet AGL. As the aircraft approaches an airport in the database, the terrain clearance floor steps down closer to terrain. Between 12 nautical miles and 15 nautical miles from the runway, the envelope steps down gradually to 400 feet AGL. The floor remains at 400 feet AGL from 12 nautical miles to 4 nautical miles, and then steps down further. The lower limit of the terrain clearance floor within 4 nautical miles of the runway is dependent on an envelope bias factor, which varies as a function of aircraft position accuracy. The terrain clearance floor function has been progressively improved since the introduction of eGPWS in the mid-1990s. Construction of the terrain clearance floor envelope in the immediate vicinity of the runway varies dependent on the eGPWS version installed on the aircraft. when the aircraft descends into the terrain clearance floor envelope, a voice alert is given. The alert is repeated with further 20% degradations in radio altitude. Additionally to the aural alert, terrain is enunciated on the navigation display in amber. The runway field clearance floor function augments the terrain clearance floor by providing an additional alert envelope for runways that are significantly higher than the surrounding terrain. The envelope is contained within a circle within 5.5 nautical miles of the runway threshold and extends to a ceiling 300 feet above airfield elevation. Penetrating the runway field clearance floor envelope results in a voice alert. This alert is repeated with further 20% decreases in radio altitude. Additionally to the aural alert, terrain is enunciated on the navigation display in amber. Look-ahead terrain alerting is accomplished based on aircraft position, flight path angle, track, and speed relative to the terrain database image ahead of the aircraft. 2 alert ribbons are constructed ahead of the aircraft to provide advanced warning of conflict with terrain and obstacles. These ribbons project down, forward, then up from the aircraft. They have a width starting at a quarter nautical mile and extend out at 3 degrees laterally. The width extends if the aircraft is turning. The look down and look up angles are a function of aircraft flight path angle. The look down distance is a function of aircraft altitude with respect to the nearest or destination runway. The look ahead distance is a function of aircraft speed and distance to the nearest runway. These measures prevent nuisance alerts when taking off or landing. A terrain conflict penetrating the caution ribbon generates a aural message. This alert is typically given 40 to 60 seconds from projected impact. Additionally to the aural alert, terrain is enunciated on the navigation display in amber. A terrain conflict penetrating the warning ribbon generates a aural message. This alert is typically given 20 to 30 seconds from projected impact. Additionally to the aural alert, terrain is enunciated on the navigation display in red. Equivalent alerts are generated in the event that an obstacle in the eGpws database should penetrate the caution or warning envelopes. Terrain data from the eGpws terrain and obstacle database can be displayed on the navigation display. The terrain display is selected by pushing the terrain switch on the EFIS control panel. The terrain display is available in the following navigation display modes: Expanded Map, Center Map, Expanded VOR, and Expanded Approach. It is not possible to have both the terrain display and the weather radar returns selected at the same time. Selecting the terrain display on deselects the weather radar automatically. The terrain display is a graphical plan view of surrounding terrain designed to enhance both vertical and horizontal situational awareness. The display design was subject to human factor studies which recommended a minimum of complexity to ensure easy interpretation. Terrain displayed on the navigation display is color-coded. Color and density vary based on the relative altitude of the aircraft to the terrain. Later versions of the eGpws incorporate the peaks display type of terrain display as a customer option selectable via a program pin. The older type of eGpws terrain display did not display terrain greater than 2,000 feet below aircraft altitude. The terrain display would therefore typically be blank during the en route portion of a flight. The peaks display feature adds further terrain information even for terrain greater than 2,000 feet below aircraft altitude. This allows the depiction of a mountain range below the aircraft in the cruise, for example, useful for situational awareness during an emergency descent. The peaks display feature also provides a digital readout at the highest and lowest terrain elevation currently displayed. Terrain is displayed on the navigation display in varying densities of green, amber, and red. Each specific color and density represents terrain below, at, and above the aircraft's altitude, based on the position of the aircraft with respect to the terrain in the database. Since the introduction of the peaks display feature, there are now two sets of rules that dictate the logic used by the system to draw terrain. The first set of rules is active when the aircraft is at a low relative altitude to the highest terrain on the terrain display, and the second set of rules is active when the aircraft is at a high relative altitude to the highest terrain on the terrain display. We will first discuss the colored terrain display indications active when the aircraft is at a low relative altitude to terrain. These indications are active when the aircraft is less than 500 feet or 250 feet with the gear down above the highest terrain in view on the display. Low-density green indicates terrain from 2,000 feet to 1,000 feet below aircraft altitude. High-density green indicates terrain from 1,000 feet to 500 feet below aircraft altitude. With the landing gear down, the high-density green envelope expands to indicate terrain from 1,000 feet to 250 feet below aircraft altitude. This reduces terrain display clutter during approach. Low-density amber indicates terrain from 500 feet below to 1,000 feet above aircraft altitude. With the landing gear down, the low-density amber envelope shrinks to indicate terrain from 250 feet below to 1,000 feet above aircraft altitude. This reduces terrain display clutter during approach. High-density amber indicates terrain from 1,000 feet to 2,000 feet above aircraft altitude, and high-density red indicates terrain greater than 2,000 feet above aircraft altitude. Solid amber indicates terrain that has triggered a look-ahead terrain caution condition, and solid red indicates terrain that has triggered a look-ahead terrain warning condition. Magenta indicates that no terrain data is available for that area, and cyan indicates terrain identified as water. This is a program pin-selectable customer option, available only with the peaks feature. Terrain greater than 2,000 feet below aircraft altitude is not indicated. These areas are black. Also, terrain within 400 feet of the nearest airfield elevation is not indicated. When the aircraft is at a high relative altitude to terrain, the Terrain Peaks feature adds additional color gradations to further define terrain below the aircraft. These indications are active when the aircraft is greater than 500 feet or 250 feet with the gear down above the highest terrain in view on the display. The shades of green displayed are based on the distribution of terrain elevations within the display range. This is a mathematical calculation based on terrain elevation and is independent of aircraft altitude. Each shade of green relates to a separate band of terrain elevations. Low-density green indicates the lower terrain band. High-density green indicates the middle terrain band, and solid green indicates the highest terrain band on the display, the peaks. Terrain below the lowest elevation band is not displayed. This is typically terrain less than 50% of aircraft altitude, but this is variable. The peaks display feature also provides a digital readout of the highest and lowest terrain elevation currently displayed. The elevation values are expressed in hundreds of feet above sea level. The color of the elevation values matches the corresponding terrain bands on the display. The terrain display automatically pops up when a look-ahead terrain alert occurs. The terrain display updates with a display sweep similar to the weather radar display. TERR is displayed in cyan on the left side of the navigation display whenever the terrain display is enabled. Controls and indications for the ground proximity warning system are located on the EFIS control panels. the primary flight displays and the HGS, the navigation displays, and the left and right forward panels. So far in this lesson, we have already covered the following controls and indications: the terrain select switch on each EFIS control panel, the below glide slope switches, the pull up and wind shear indications on the PFD and HGS, and the eGPWS terrain display and the terrain annunciation. The remainder of the GPWS controls and indications are located on the right forward panel. The 3 capped inhibit switches allow the flight crew to manually inhibit GPWS alerts. All 3 switches are capped to the normal position. The 3 capped inhibit switches allow the flight crew to manually inhibit GPWS alerts. All 3 switches are capped to the normal position. The flap inhibit switch simulates a flap's landing position in the GPWC, inhibiting the mode 4B alert. The gear inhibit switch simulates the landing gear in the extended position, inhibiting the mode 4A alert. The terrain inhibit switch inhibits the look ahead and alerts. It also inhibits the terrain display. The in-op light illuminates under 4 sets of conditions. If the GPWC has suffered a malfunction or power loss, the GPWC cannot calculate wind shear conditions, a failure of a critical input to the GPWC has occurred, or if a GPWS self-test is active. The system test switch initiates a self-test of the system. Pushing the system test switch quickly gives a short confidence test, and pushing a switch for 5 seconds gives a full vocabulary test. Several indications on the flight deck cycle on and off as the test completes. The below glide slope switches, the GPWS in-op light, the pull-up alert on the PFD and HGS, the wind shear alert on the PFD and HGS, the wind shear annunciation on the ND, the terrain fail annunciation on the ND, the terrain test annunciation on the ND, and the eGPWS terrain display test pattern on the ND. The ground proximity warning system is a critical fallback in the event of loss of situational awareness by the pilots. It provides alerts throughout the flight of developing conflicts with terrain. The addition of look-ahead terrain alerting and the other enhanced functions of eGPWS adds a further safety net that has had proven success over the past decade. We've covered a lot in this lesson, it's been a long one, but let's summarize now what we've been through in the lesson summary. We started with a brief overview of the background, objectives, and functions of the GPWS and eGPWS. We covered the Ground Proximity Warning Computer, or GPWC, and we ran through the 7 GPWS operating modes and their sub-modes. We'll quickly summarize the 7 modes briefly now. Mode 1 is for excessive descent rate. Mode 2 for excessive terrain closure rate. Mode 3 for excessive altitude loss after takeoff or go-around. Mode 4 for unsafe terrain clearance. Mode 5 for excessive deviation below ILS glide slope. Mode 6 for advisory callouts, and Mode 7 reactive wind shear. We also ran through the enhanced functions of the GPWS: envelope modulation, terrain clearance floor, runway field clearance floor, and look-ahead terrain alerting. We discussed the terrain display on the ND, and we ran through peaks mode. We then concluded with an overview of the controls and indications relating to the GPWS on the 737 next generation.